Hello friends, I am Dr. Balvinder Singh Taliwal. In this video lecture, I will discuss basics of digital filter design. The purpose of this lecture is to provide a common framework for digital filter design. A simple step-by-step guide for designing digital filters from specifications to implementation is discussed. A filter is essentially a system or network that selectively changes the wave shape, amplitude frequency and or phase frequency characteristics of a signal in a desired manner. Common filtering objectives are to improve the quality of a signal by removing or reducing noise, to extract information from signals, or to separate two or more signals previously combined to make efficient use of an available communication channel. A digital filter is a mathematical algorithm implemented in hardware and or software that operates on a digital input signal to produce a digital output signal for the purpose of achieving a filtering objective. The term digital filter refers to the specific hardware or software routine that performs the filtering algorithm. A simplified block diagram of a real-time digital filter with analog input and output signals is shown in the figure. The band-limited analog signal is sampled periodically and converted into a series of digital samples by first two blocks of the block diagram. Then the digital processor implements the filtering operation, mapping the input sequence xn into the output sequence yn in accordance with a computational algorithm for the filter. The fourth block, DAC, which stands for digital to analog converter, converts the digitally filtered output into analog values, which are then analog filtered to smooth and remove unwanted high frequency components. Digital filters play very important roles in digital signal processing. Compared with analog filters, they are preferred in a number of applications because of one or more of the following advantages. First, digital filters can have characteristics which are not possible with analog filters, such as a truly linear phase response. Second advantage, unlike analog filters, the performance of digital filters does not vary with the environmental changes, for example thermal variations. This eliminates the need to calibrate periodically. Also, the frequency response of a digital filter can be automatically adjusted if it is implemented using a programmable processor, which is why they are widely used in adaptive filters. Several input signals or channels can be filtered by one digital filter without the need to replicate the hardware. Both filtered and unfiltered data can be saved for further use. Advantage can be readily taken of the tremendous advancements in VLSI technology to fabricate digital filters and to make them small in size, to consume low power and to keep the cost down. In practice, the precision achievable with analog filters is restricted. For example, typically a maximum of only about 60 to 70 dB stop band attenuation is possible with active filters designed with off-the-shelf components. With digital filters, the precision is limited only by the word length used. Digital filters can be used at very low frequencies found in many biomedical applications, for example, where the use of analog filters is impractical. Also, digital filters can be made to work over a wide range of frequencies by a mere change to the sampling frequency. However, there are certain limitations of digital filters. First is speed limitation. The maximum bandwidth of signals that digital filters can handle in real time is much lower than for analog filters. In real time situations, analog digital analog conversion processes introduce a speed constraint on the digital filter performance. The conversion time of the ADC and the settling time of the DAC limit the highest frequency that can be processed. Further, the speed of operation of a digital filter depends on the speed of the digital processor used and on the number of arithmetic operations that must be performed for the filtering algorithm, which increases as the filter response is made tighter. Second limitation is related to finite word length effects. Digital filters are subject to analog to digital conversion noise resulting from quantizing a continuous signal and to round off noise occurred during computation. With higher order recursive filters, the accumulation of round off noise could lead to instability. Third limitation is related to long design and development times. The design and development times for digital filters can be much longer than for analog filters. However, once developed, the hardware and or software can be used for other filtering or DSP tasks with little or no modification. Good computer-aided design support can make the design of digital filters an enjoyable task. Digital filters are broadly divided into two classes, namely infinite duration impulse response, abbreviated as IIR, and finite duration impulse response, abbreviated as FIR filters. Either type of filter in its basic form can be represented by its impulse response sequence, denoted by symbol HK. The input and output signals to the filter are related by the convolution sum, which is given in equations shown on the screen for the IIR as well as for the FIR. It is evident from these equations that for IIR filters, the impulse response is of infinite duration, whereas for FIR it is of finite duration, since HK for the FIR has only n values. In practice, it is not feasible to compute the output of the IIR filter using the equation shown on earlier screen, because the length of its impulse response is too long or infinite in theoretical equation. Instead, the IIR filtering equation is expressed in a recursive form as shown here on the screen, where the AK and BK are the coefficients of the filter. This equation is known as difference equation for the IIR filter. In particular, the values of AK and BK are often very important objectives of most filter design problems, and for FIR case, the values of HK are important. From equation 3, which is recursive equation of IIR filter, we can see the current output sample Yn is a function of past outputs as well as present and past input samples. That is, the IIR is a feedback system of some sort. And if we compare this equation with the equation of FIR filter, in that filter, the current output sample is a function only of past and present values of the input. Therefore, no feedback is used in case of FIR systems. This screen shows the alternative representations for the FIR and IIR filters. These are the transfer functions for these filters and are very useful in evaluating their frequency responses. HZ is also known as system function or transfer function. The choice between FIR and IIR filters depends largely on the relative advantages of the two filter types. FIR filters can have exactly linear phase response. The implication of this is that no phase distortion is introduced into the signal by the filter. This is an important requirement in many applications. For example, data transmission, biomedicine, digital audio and image processing. The phase response of IIR filters are non-linear, especially at the band edges. Also, the FIR filters are realized non-recursively, that is by direct evaluation of the input-output relationship which we have discussed earlier, and these filters realized in non-recursive form are always stable. However, the stability of IIR filters cannot always be guaranteed because of the recursive nature of implementation. The effects of using a limited number of bits to implement filters such as round-off noise and coefficient quantization errors are much less severe in FIR than in IIR. FIR requires more coefficients for sharp cutoff filters than IIR. Thus, for a given amplitude response specification, more processing time and storage will be required for FIR implementation. However, one can readily take advantage of the computational speed of the FFT and multi-rate techniques to improve significantly the efficiency of FIR implementations. Analog filters can be readily transformed into equivalent IIR digital filters meeting similar specifications. This is not possible with FIR filters as they have no analog counterpart. However, with FIR it is easier to synthesize filters of arbitrary frequency responses. In general, FIR is algebraically more difficult to synthesize if CADS port is not available. From this discussion, we can form a broad guideline on when to use FIR or IIR. For example, use IIR when the only important requirements are sharp cutoff filters and high throughput, as IIR filters, especially those using elliptical characteristics, will give fewer coefficients than FIR. And use FIR if the number of filter coefficients is not too large, and in particular if little or no phase distortion is desired. If we want to design a digital filter, then it involves 5 steps. First is specifications of the filter requirements. Second is calculation of filter coefficients. Third is representation of the filter via suitable structure. Fourth is analysis of the effects of finite word length on filter performance. Implementation of filter in software and or hardware is the last step. I will explain or discuss these steps in detail in my next video. And for this lecture I refer to book name shown on this screen. Thanks for watching the lecture.